Now let's look at an example of application of Markov process we just discussed. This example is from the textbook, so we may not be able to complete the whole example, but we're going to start at least to do some of it. Okay, so let's look at the problem. Here we have a salesman. Is responsible for sales for certain product in towns 1, 2, and 3. The length of time he spends in each town for each of his continuous stay forms a sequence of independent random variable. Now, if we think about this, so this part over here is telling us about the sojourn time. So it's Tn plus 1 minus Tn. And it's telling us these are independent random variables, and we also have later on saying that's exponential distribution. So this is one of the two assumptions for the Markov process, right? Let A1, A2, A3 denote the amount of time each continuous stay in towns A, B, C respectively. We have that they obey the exponential distribution with parameters lambda 1, lambda 2, lambda 3 are given. Now, if you try to recall, the rate over here is 0.5, 1, and 2, 3. These rates mean the expected amount of time spent in each town is 1 over these lambdas. So we can see actually in town 1, so in town 1, he is going to stay on average 2 times weeks, 2 weeks. Okay, so this is what we have. And in town 2, he is going to stay just for 1 week. And in town 3, he will stay 1.5 weeks on the expected length of stay. Okay. Now, the next paragraph tells us exactly about the Markov matrix for the embedded Markov chain. And let's look at it, and then we can find out the embedded Markov chains matrix. It says if he leaves town 1, he has a 50-50 chance to go to either town 2 or town 3. So let's try to get the Markov matrix. And this is the one we have. So these are states 1 and 2 and 3. This is the Markov matrix for the embedded Markov chain. If he leaves town 1, then he is not going to be staying in town 1. And then with 1/2 and 1/2 chance, he's going to go to town 2 or town 3. And when he leaves town 2, it says, he prefers to go back to town 1, maybe his hometown, with a probability 0.75. So when he leaves town 2, he's going to go back to town 1 more likely, but he can also go to town 3. And the same thing for town 3. So he's likely to go back to town 1 and also town 2, but town 3. Now, if you look at this Markov matrix, we will have an irreducible set of states because you can go from town 1 to town 2, right? And you can go from town 2 to town 3, right? And you can go from town 3 to town 1. So we see that all these 3 states, they actually are on the loop. So we know this is irreducible. So this is, of course, in the assumption. Otherwise, our calculation will not be valid. Okay. Now look at the first question, what we have. Find the Markov matrix for the embedded Markov chain. So this is done. Okay. And find the sojourn rates. We know that lambda 1 is 0.5 and lambda 2 is 1 and lambda 3 is 2/3. So when these data is given, then the Markov process is determined. Now we can find the generator matrix G. how can you find the generator matrix G? We recall that on the main diagonal, we just put these rates over there, but with a negative sign. So we have negative 1/2, okay, and negative 1, and negative 2/3. Now, off diagonal, we need to multiply these rates by the off diagonal numbers. So we have 1/2 times 1/2, 1/2 is 1/4. And you will see that this matrix is no longer a Markov matrix, but it's still special. If you look at each row, if you add them up, it's 0. Okay, so that's a good way to check whether you're getting the generator matrix correct. So lambda 2 is 1, so there's no change. And then we have over here is the 3/4, and then this is 1/4. Just multiply it by 1. And the last one multiplied by 2/3. So 2/3 times 3/4, we have again 2/4, that's 1/2. Okay, and 1/4 times 2/3 is going to be 1/6. So this is the generator matrix. And our first question is completely solved. Now let's look at the second one. It says, on average, what is the percentage of his time spent in town 1, town 2, and town 3? Now, we already know how long on average he's going to stay in town 1, that's 2, 1, and 3/2. So we have an idea, but also we need to somehow consider this the Markov matrix over here as well. So it's a combination of these two. And this question over here is exactly asking for pi. So for number 2, it's really asking for pi. I is equal to 1 and 2 and 3. The percentage of time spent in state I. That's what we are looking at. Now, how to find p? We say we find p by solving this equation called pg is equal to 0. And to do that, we just need to look at pg transpose, and p transpose is equal to 0. What it means is that we actually solve negative 1/2, 1/4, and 1/4, and 3/4, negative 1, negative 4, and negative 1/2, 1/6, negative 3. This one over here, but transpose. And then we have P1, P2, P3. You may say why we do this, because we always use row reduction, and this way we can use row reduction. So now what we have over here, make sure that we make the transpose. Then we have 1/2, 1/4, and 1/4, and then we have 3/4, negative 1, and 1/4, and then 1/2, and 1/6, and negative 2/3. And we have P1, P2, and P3 is equal to 0. Now remember, if you add up these numbers, you get 0. So if you use a row reduction, you know there is one free variable. There's always a free variable. So we can just say, okay, we can take P3 free variable, and then we only solve the first 2 equations. So we do the row reduction to the first 2 rows. Normally we don't like fractions, so we can actually multiply 4 over here. So we have negative 2 and 3 and then 2. And then multiply 4 over here, we have 1 and negative 4 and then 2/3, right? That's the one. Now we can multiply the second row by 2 and add it to the first one. So we can say 2 times row 2 and add it up to the first one. Then we have, this is going to be 0. 2 times negative 4 is negative 8, plus 3 is going to be negative 5. 2 times 2/3 is going to be 4/3. Add 2, that's going to be 10/3. And then here we have 1, negative 4, and 2/3. You may say this is not standard kind of row reduction, but it's fine because we just want to solve for these variables. So from the first equation, we have negative 5 p2 plus 10/3 and p3 is equal to 0. And that means we have p2 is equal to 2/3 p3. Now for convenience, we can choose p3 because free variable, p3, we can choose 3. You may say this is not a probability, but don't worry, we will actually normalize it in the last step. So if we choose p3 to be 3, then p2 is going to be 2, right? And then last equation we have over here is p1 is equal to 4p2 minus 2/3 of p3. So when we plug it in, then we have 8 and minus 2, which is 6. So now we have the vector over here. So we have the vector p1, p2, and p3. And then we have the 6 and 2 and 3. Don't forget to normalize because otherwise it's not going to be right. We need to have probability or percentage. So this is going to be 6 plus 2 plus 3 is 11. So we have over here 6 over 11 and 2 over 11 and then 3 over 11. So these components over here, they give us the percentage of time this salesman spent in town 1, town 2, and town 3 over long run. All right, now let's look at the last question. It says, if he was making $8 per day in town 1, $100 per day in town 2, and $125 per day in town 3, what is his average profit per week in the long run? Now here, there is a catch. He's making $80 per day, so how much dollars per week? We assume he works 5 days a week, so we have to multiply 5 by all these numbers. So we have third part to find out expected profit. We will say, okay, in town 1, he's going to spend 6/11 of his time. And in town 1, he's going to make $80 times 5 per week. Okay, and then in town 2 is 2 over 11, and it's 100 times 5. And town 3 is going to be 3 over 11, and it's going to be 125 times 5. So, and that's going to be the profit per week. Profit per week on average or long run. Okay. The last question, question 4, involves the jump cost, and the solution is in the textbook, and it's pretty just straightforward, plug in the formula calculation, so we're gonna skip that.